Hello and welcome back. If you follow the channel, you know that we are trying to replicate the famous Hafele and Keating experiment that directly measured time dilation as predicted by Einstein's theory of relativity by flying HP 5061A atomic clocks around the world in 1971. Like Hafele and Keating, we can't just use one clock to give us the needed precision. Instead, we need to average several clocks. The original experiment used 4 flying clocks, plus another bunch of much larger and more precise ones on the ground for reference. So far, we have rounded up 4 atomic clocks from eBay of the same model that had been used by Hafele and Keating. But as expected, they are old and tired, and we have been struggling to make them work. First of all, we needed to repair them so they just worked. But that's not enough. We also need to bring them back within the required precision for the experiment, which is proving to be a challenge. The goal is to have them stay within a few nanoseconds of each other over 2 days, which means 0.1 part per trillion stability over that time frame, or in techno parlance, less than 10 to the minus 13 Allan variance at 100,000 seconds. And that's very hard. It's far beyond the reach of GPS-stabilized clocks, even the expensive rubidium kind, and somewhere below the limit of standard tube clocks, and barely above that of high-performance tube clocks. I strongly suspect that Hafele and Keating had clocks equipped with high-performance tubes, which are rare and much shorter-lived than their standard-issue cousins. On top of that, it is probable that HP had hand-selected their best clocks for this experiment. Needless to say, we had to dig deep into the innards of this intimidating instrument to approach our goal. Our first semi-successful repair was actually on the very clock we are going to revisit today. It had worked for a short while, then failed right before the start of our first clock stability experiments. We found that something had happened to its multiplier, which we were fortunately able to repair. We were then able to go on with our first stability experiment, comparing it to another clock that had worked well from the get-go and had a high-performance tube in it. Unfortunately, that first atomic clock stability campaign did not work out as expected. The repaired clock was found wandering around by many tens of nanoseconds, seemingly randomly, nowhere good enough for our experiment. I reluctantly concluded that something more fundamental must have been wrong with this clock. Most probably, its tube was spent, and although it was still quite good for amateur lab use, it wasn't good enough for our experiment. So I set it aside and worked on the next one. Our second repair involved a clock that didn't work at all. You can recognize this one easily because it's the only one that has the optional digital clock display on it. All the other ones are frequency standards with no time indication. To our relief, we found that the signal from the tube was still good, but for some reason the clock stubbornly refused to lock on the cesium absorption line. A lengthy adventure ensued, which led us to the phase detector and then eventually to a single bad coaxial cable. A new cable revived it temporarily, but it promptly broke down again. This time it was a semi-bad transistor in the tube signal amplifier. However, after these 2 repairs, we got our first encouraging results. Drift curves between our reference clock and our repaired clock were nice and straight. Something we should be able to correct for by adjusting the C field. But sadly, when I tried that, I found to my dismay that something else might be wrong with the C field circuitry. I was now chasing 0.1 part per trillion, and every little thing started to matter. As explained in the mind-numbing Zeeman alignment episode, the C field is a weak magnetic field used to fine-tune the clock. While looking at the C field issue, I discovered 2 important things. First, that this clock had an upgraded C field control circuitry with better stability, which was mighty good news. Problem is, said upgraded circuit wasn't working properly. The root cause was a bad electrolytic cap. I also found that all of our other clocks had the same upgraded C field circuit and the same bad cap problem. So I changed the offending caps in all of the machines, and things finally started to look up. I was able to get much straighter curves for 3 of our 4 clocks, with drifts in the single-digit nanosecond range. Which leaves us with the one clock that is still not working, the initial one that I had given up on, and which did not improve after changing its cap. However, now that I am more familiar with the clocks, I decided that I could take another stab at it and confirm whether a weak tube signal was indeed to blame. For that, I instrumented the clock as I had previously done, connecting myself to the phase detector. And that's when things became interesting. So now that I am a little bit more familiar with the clocks, I am revisiting the one I tossed out as not good, and the one that was hopping in frequency before, and sure enough, the caps in the power supplies were bad. Actually, they were all bad in all the clocks, so I changed them. So the C field was not well regulated, and then you can see it's unstable. That's normal, but when it goes the big one, that's not normal, and it shouldn't do that. So by the way, just to document it, what I am doing is first changing the 3 caps over here on the C field power supply, and then I am hooking 3 cables. One is on the AC amplifier output to monitor the signal out of the tube. One is the 137 Hertz modulation, so you can tune it to 137 Hertz. It's over here. And one is the phase detector. You can tune the 0 here and the symmetry of the phase over here. Let's review how some of the clock circuitry works so you can understand what I'm looking at here. All of the cesium quantum mechanics magic happens in the tube, and you don't need to worry about it right now. If you want to know more, I have a previous episode that will tell you all about it, link in the doodly-doo. But for this episode, all you need to know is that we interrogate the tube with a microwave frequency at 9.192631770 GHz. Actually, not exactly that either, because of the C field and the Z-man effect, but we'll skip over that for this explanation. Despite the complicated physics happening inside the tube, the result is very simple. We get a current at the output that peaks at the cesium resonance frequency. The output signal versus input frequency curve looks like this. The name of the game is to lock the microwave frequency right on top of the peak resonance using a servo loop. This frequency then becomes our atomic derived reference, which we can then divide to our heart's content to give us a bunch of standard reference frequencies, namely 5 MHz, 1 MHz and 100 kHz in this instrument, plus an exact second if you have the clock option. But how does the locking loop work? This is done by continuously probing our position on the peak by dithering the microwave frequency. This dithering or wobbling in the frequency is very slight and quite slow, at 137 Hz to be exact. When we are detuned on one side of the peak, we'll get a 137 Hz modulation in our output signal that's in phase with the dithering. If we are on the other side of the peak, we'll also get a 137 Hz tone, but out of phase with the dithering. And if we are well centered, we won't get any 137 Hz at all. Instead, we'll get a little bit of second harmonic. The absence of the 137 Hz fundamental tone and the detection of the second harmonic tone tells us that we are locked on the atomic resonance and will turn on our coveted green light. Here we can see how that works on the oscilloscope. The dithering ramp is a sawtooth in yellow and the output of the tube is in green. The clock is operating in open loop and I am directly controlling the center microwave frequency using the front panel knob. When we are on one side of the resonance, the tube signal looks like a sine wave. As I move the mean frequency across the peak, the green signal goes to 0, then reappears as I go to the other side of the peak. If you watch the phase of the yellow and the green closely, you'll see that it goes from mostly in phase to mostly out of phase when I go through the peak. In regular closed-loop operation, the 137 Hz tone is monitored by the phase detector, which can tell on which side of a peak we are. The detector output, which is the error signal, is fed back to the microwave generator, actively keeping the frequency right on top of the cesium peak. In this oscillogram of our broken clock, yellow is now the output of the tube, green is the output of the phase detector, and blue is the frequency dither sawtooth. The clock is operated in closed loop, and we see a noisy signal at the output of the tube with only second harmonic left in it. The phase detector output is mostly noise around 0 too. And that's how it should be for a locked clock. We are locked right on top of the cesium line. However, the signals go wild as I am talking. That definitely shouldn't happen. That's precisely what's causing the random shift we see in our clock frequency. What's going on? At first I thought it was the tube that was noisy, but if I put it out of in open loop, yo! So look at that yellow signal. I have plenty of signal out of the tube. So it's not the tube. What I think is happening, okay, it's locked. Okay, if I turn it, it will be locked. What I think is happening is my switch is noisy. Look at that. So, and it's a wafer switch, and the switch is straight into the feedback loop. Oh no, until now we had looked at the block diagram for babies. Here is the one for adults. Reality is a bit more complicated. We recognize our magic cesium tube. Its output feeds the amplifier, the very one that let us down in the last episode with its bad transistor. The amp filters out the 137 Hz tone, which then goes to the phase detector, which also let us down in the previous episode. Although, to be fair, it was really the bad cable between the amplifier and the detector that prevented it from working. The output of the phase detector then goes through an op-amp. It is wired as an integrator to smooth out the loop operation. The output of the op-amp then goes to the oscillator, which controls the RF generation chain and closes the loop. But our switch, called S2, also appears in the middle of the loop. And not only once, here it is a second time, and a third time, and a fourth time. It's everywhere. It's a multi-position switch with several wafers, and it's smack in the middle of the control loop. In particular, it's in the feedback path of the operational amplifier. If the switch goes even slightly bad, that's deadly. If you follow the channel, you probably know that we've been killed by bad switches in instrumentation op-amps feedback path several times. I guess we're being victims of it once more. An HP switch that's in an analog op-amp loop causes all kinds of problems. So I think what was wrong with that one is the caps, of course, but then that my switch is not good. And then if I clean that one up, it's going to work again. And the switch is right there, the blue wafers that you see. And so that's an open wafer switch, and that one already killed us recently in the DVM that we repaired. Exact same problem, a wafer switch that is in the feedback loop of an op-amp, of an analog op-amp, and if that develops some resistance, it's toast. It killed our ohm meter measurement in the DVM, and here I think it's killing our frequency. So I need to put some contact cleaner on that one. Where is the contact? And the oxide gold repairs all evil. And after a little bit of deoxide, it's not doing it anymore. It's fine. That was our problem. And I'm going to demonstrate how to do the phase adjustment. So I took out the input of the tube, that's J3. And then you max out the gain of the scope, and I'm going to go into averaging, And then once you, oh, I should remove two. I should do this. I should remove modulation. Get it somewhat to 0. Yeah, it's about 0. Then you want that at 137 hertz, and it's once pretty much right on. It's 137.03. Then you turn modulation on. And I have no beam intensity. I do. Oh, I have no beam intensity because I have to reconnect it. There we go. We do have beam signal, plenty of it. So I should be able to lock it. Let me get back to this. I should be able to get, so now it's super easy to lock it when you do that because you see the error signal. So it's here, there, okay. So what I'm going to do here is make sure my phase detector is correct, and I can tell it's not. So you have to balance the two arms of the phase. This has to be symmetric. It's not. There we go. Ooh, this one was way out of adjustment. So it's too far that way is not good. Too far that way is not good. So you want it kind of nice and symmetric. And then it goes through 0 and goes to the other side. So now my bet is that it will lock super easily. And it's already extinguished here. So if I put to operation, blah, it locked. Boom. I see it. It's averaging. Wait a second. I got lost here. Okay. Yeah, it's slightly less noisy than the other clock. So if I take it open loop, yeah, I have a nicely balanced phase detector. Ooh, perfect. Perfect. Very balanced. Okay. And now I'm going to get it back to closed loop. And I can tell it's locking right away. I wish they had a scope embedded in the instrument. When you're just doing it from the front panel, it's quite unobvious what's happening, but when you look at the signal, the phase detector, you know exactly what's happening. Okay, I'm locked on the Cesium line. Alright, time for a new run of stability measurements. I am measuring clock 2, the one we think we just repaired, against clock 1, our stud clock reference with the high performance tube. Ignore clock 3 and 4, they are not powered up at the moment. So we'll see first how they do on short runs, and then I'll zero in on the C field, and then we'll do some long runs. Okay, it's been 2 hours and I've drifted by minus 3.5 nanoseconds, so it's pretty close. So I need to slow it down, which means I need to turn the C field in the negative direction. I always get that wrong. And it's pretty close, so I'm going to do it maybe 2 graduations. It's very, 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 very close. Actually 2 graduations, 1 tick, which is 2 units. So I am at 452 now. And now I'm doing it the refined way, so I will also degauss it. We also repaired the degausser, which is specific to this clock, in another episode. It's used to erase the traces of the previous magnetic setting and make sure your C field is perfectly uniform across the tube. So I'm also going to degauss it, so the field is nice and uniform. When we're that close, that's the right time to do it. Adds 15 minutes. After degaussing and a first trial run. Well, it has been about 5 hours, and look at that.
I think we repaired it. That was our wayward clock, and now it's super straight. It has moved only 2 nanoseconds. That's after the first adjustment only. I'm going to be hard pressed to do any better than that. I'm going to let it run overnight and see if it keeps being straight, but I don't see the noise that I had before. I don't see the wild frequency swings I had before. So I think things are looking up. Alright, I let it run about 20 hours and the results are in, and they're a bit puzzling. So I run it for 2 hours, and then I estimated how much I had to change the C field to get it at 0, and I did it right the first time. So it started good, and then over the 20 hours we have 8 nanoseconds, which is not bad, but the way it does it, it gets stable, and I have a jump here, then I have another jump here and an anti-jump, and then it gets stable again. So it's much cleaner, but I still have this bizarre jumps. That long part here, I don't have a problem with it. It's nice and stable. The one I have a problem with is right here. What's that about? And then you see there's another one over here. So it still has those discrete jumps from time to time. Then when I look at the indication here, it's not at 0 anymore. After my 2 repairs, there is still something wrong. And my best theory right now is that it's the quartz overnight oscillator that's not good, and that it moved, and that in order to catch it, the signal, the control signal had to move on the side. So my temptation would be to bring it back to 0 and let it run, and let's see if that moves away from 0. And I'll let it run a couple more hours, and it started good, was nice and flat after that hiccup, no more hiccups. So I thought it was going to go perfect, and then, dang it, another hiccup, about the same, moves by 5 nanoseconds all of a sudden. And if I look at the clock, it's this one that we are seeing at an angle, but it's smack on 0. So my brilliant theory that it was the quartz oscillator, the crystal oscillator that was moving and that required pulling back, it's not working because I had it at 0 before and it's still at 0, and I got a frequency burp anyhow. And that's really annoying because you can tell this is a high performance clock. It doesn't move hardly at all. It just jumps. It has frequency burps, and I have no idea what would cause this. I don't know what experiment to make, so I will conclude that we have 3 clocks that we can rely on for doing the experiment. The 3 at the bottom here, and that this one, well, it's suspect. It has frequency hops that we can't explain. Well, that's a bit of a bittersweet ending for this episode. I really thought we had repaired our much-needed 4th clock. Well, we repaired something, but there are still unexplained gremlins in it. The gremlins are getting smaller and smaller though. Of course, if we had paid enough $1 million and a large bus to get 2 newfangled fountain clocks, we'd have been done with this experiment a long time ago. But this shows you the difficulty of the original experiment with clocks that could barely do it, and how everything gets harder and harder when you are doing metrology and bumping into the limits of your instruments. So we are not out of the woods yet, but I still hope to see you in the next episode.